Hello, pre-calc students. This is Mr. Beck. Today we're going to be finishing our discussion with 6.2. 6.2, if you remember, was introducing all six trigonometric functions: sine, cosine, tangent, cosecant, secant, and cotangent. But then we're also going to be talking today about, we're building off that unit circle that we did yesterday. We're going to talk about the different relationships around the circle, comparing x and y values and slopes. And then we're going to take it and we're going to look at the geometrical aspect of the unit circle, or really just any circle in general. So to begin with, I do want to talk about how do we find some of these values in the calculator, because remember last time we set up and we found specific values, our 30, 45, 60 degree angles, which are our pi over 6, pi over 4, and pi over 3 angles. So we found all those individual values. Well, what happens if we have some other values, in this case, such as the sine of 194 degrees? As you're using the calculator, one of the things that you are going to find is the calculators will all have a button. That button will talk about degrees, radians, and gradients. Usually you'll see it as a DRG, where the D stands for degrees, the R stands for the radians, and the G stands for gradients. We are not going to be using gradients at all in here. We're going to be focusing primarily on degrees and radians. So when it comes to degrees, sine of 194 degrees, if you type it in your calculator, we always round to 3 decimal places. We get negative 0.242. In my mind, what I don't like about the calculators is it's like, okay, great, I have this decimal value. What does this decimal value actually represent? This is a ratio, and it's still a ratio, but it's a ratio in decimal form. Because it's a ratio, I want to try to process what does it actually mean. So if I draw out 194 degrees, if you remember the unit circle, 194 degrees, a little bit over 180. So I'm looking at quadrant 3, and it's just slightly below the x-axis. So to have a y value that's pretty close to 0, but just slightly negative, makes sense to me. Tangent of 322 degrees. If you remember, tangent is equivalent to the slope. So the slope at 322 degrees. To have that at negative 0.0781 in the calculator seems to make sense to me. And again, all of these I'm just trying to figure out what makes sense and why these decimal values would come out of it. 140 degrees, if I look at cosecant of 140 degrees, that means I need the reciprocal of the sine function. Well, sine of 140 degrees, we're looking at quadrant 1. So if you look at 150 degrees, the sine of 150 degrees is 1/2. If you reciprocate 1/2, you get 2. So if you have a number that's slightly bigger than 1/2 and reciprocate it, I should have a decimal value that's slightly smaller than 2, or in this case, 1.556. So in the calculator, we do have to type 1 over the sine of 140 degrees. Some calculators require you to do the sine of 140 degrees first and then do 1 over that. Most important thing is if you see sine to the negative first, do not use that button. That's something we're going to be exploring in chapter 7. So always type it in as 1 divided by the sine, and make sure you have your brackets there, 140 degrees. Cotangent, same thing we're going to do. It's 1 over tangent. Tangent of 97 degrees is, it's a very, very steep line. So the reciprocal of a steep slope should be a very, very small slope. Cotangent of 2 pi over 9, suddenly the fact that 2 pi over 9, that pi should clue us in that we're radians, but more importantly, where A through D all had degree marks, this does not have a degree mark, so that's your clue in that it's radians. So 1 divided by tangent of 2 pi over 9, make sure you know where your pi button is, 1.192. Secant is a reciprocal of cosine, so 1 over cosine of 3 pi over 5. 3 pi over 5 is in quadrant 2. So we should have a negative value for x. That means we have a negative value for cosine, which is why our cosine of 3 pi over 5 is negative. G, cosecant of negative 6 pi over 11. Negative 6 pi over 11, we're looking at in quadrant 3. And sine is negative there because the y value is negative. So 1 over the sine of that, the fact that I get a negative answer out of that makes some sense to me. Now this one confuses people. Secant of negative 24. A lot of people are like, wait a second, that looks like a degree. It doesn't look like radian, but there is no degree mark. And since there's no degree mark, we have to treat it as a radian. So 1 over cosine of 24 radians is 2.357. Keep in mind, I know a lot of people get concerned the fact that there is no degree mark there, and they think, hey, that looks more like a degree. Keep in mind that 1 radian around the circle makes sense. That 1 radian around the circle is a certain distance away. So 1 radian around the circle, I think it's like 57 degrees-ish, somewhere around there. But 1 radian does have an actual degree value. So to have 24 radians means we're just going around the circle many, many times. So next set of problems, what we're looking at is find the sine of 35 degrees. So using the calculator, we find the sine of 35 degrees, which is 0.574. Now that 35 degrees, remember, is the y value because we're looking at sine. This is the y value on the unit circle. Our next directions say find 2 coterminal angles. If you remember, coterminal angles mean what happens when we take that angle and we go a whole another 360 degrees. So if we add 360 degrees, which is our coterminal, we get 395. If we subtract 360 degrees, meaning we go backwards, we get negative 325. So our 2 coterminal angles are going to be 395 or negative 325. Honestly, we can go further if we wanted to. We can either add more 360 to the 395 or keep subtracting 360 from the negative 325. But adding and subtracting 360, meaning adding and subtracting 2 pi, will get us to the exact same values. If you type in the calculator, sine of 395, that's equal to 0.574 as well. Now, next direction is find an angle in quadrant 2 whose sine ratio is the same. Well, if I want the same sine ratio, what I want to do is I want to look and say, okay, that 35-degree angle produces a certain y value. That y value is also replicated in quadrant 2. So I'm going to use that 35 degrees as sort of a reference angle. So if I go 35 degrees back off of 180 degrees, then I get 145 degrees. And we could check in the calculator, and indeed, the sine of 145 degrees is 0.574 as well. So why is it true? It's the same y value on the unit circle. So that angle off of the x-axis is going to produce the same y value. Same kind of problem on number 3. The cosine of 35 degrees is 0.819. So 2 coterminal, it's those same 2 angles that we have from part A. An angle between 0 and 360 who has the same cosine ratio. Well, in this case, so I'm not sure why I put 0.7 here as the x. That was my hesitation there. So my x value that I have here is actually 0.819. Let's go ahead and put that there. Okay, so if I want to have the same cosine ratio, I need to have the same x value. So that same x value, what I'm going to be looking at is the same x value is going to occur in quadrant 4. So if I take 360 minus that 35 degrees, I'm going to get 325 degrees. And if we check in the calculator, the cosine of 325 degrees is indeed the 0.819 as well. So what that means is if I want to know an exact cosine or a degree that gives me an angle that gives me the same sine or the cosine ratio, what I'll be looking at is what angle off the x-axis is going to give me the same x value or the y value. So y value for the sine, the x value for the cosine. But what about tangent? In order for us to work with tangent, then first in the calculator, tangent of 35 degrees is 0.700. Those zeros are actually important, so make sure you write it. Same 2 coterminal angles. That's not any different. But to have the same tangent ratio means I need to have the same slope. So to have the same slope, we have to add 180 degrees to my 35, which is 215 degrees. And if we check in the calculator, tangent 250 degrees is the 0.700. What we're doing with these kind of problems is we are using the symmetry of the circle, we're using the angles, and we're using a geometrical relationship to help us understand what the different trig function values are, or the trig ratios are. We should really start calling them ratios because remember, what comes out of a trig function is the ratio. What goes into a trig function is an angle. So some properties of the trig functions. What I showed on those problems there, if we take our coterminal angles, meaning we add or subtract 2 pi to any of these, we're going to end up getting the exact same sine ratio, cosine ratio, secant and cosecant. Tangent, it'll be the same also, but tangent more specifically because of the same slope. All you have to do is add just any form of pi, and you're going to be okay. If you had 2 pi, obviously you're going to be the same coterminal, but if you had pi, it's what we call periodic. And we'll get into the periodic nature of sine, cosine, and tangent as we get into 6.4. Even and odd properties. So looking at even and odd properties, this is going to be very beneficial. Sine of negative theta. Sine is an odd function, so sine of negative theta is the negative value of the sine of theta. That's really what odd functions are modeled. So the reason why that is because if you take a look at any angle here, the sine of that angle is going to be the y value. So if you take the negative of that angle, you end up with the negative of the y value. Hence the fact that this is an odd function. And when it comes to tangent, same kind of thing. If we take that angle, we have a certain slope. If we take the negative of the angle, we have the negative of that slope. So because it's the negative of that slope, tangent of negative theta is going to be the negative of the tangent of theta. Hence, it's an odd function. And if sine and tangent are odd, then their reciprocals, cosecant and cotangent, are also odd. Cosine, however, is an even function, as you see in like the reddish pinkish color there. Cosine is an even function because if you notice, you have the exact same x value. So whether we have positive theta or negative theta, we're going to end up with the exact same x value because it's the same degree off of the x-axis. So the x position is going to be the same. We could use that to our benefit and throw a couple different types of problems at you. If I know that the sine ratio is 1/4, one of the things I like to do is I like to picture it. So if the sine ratio is 1/4, I'm just picking an angle in quadrant 1 that has a y value of 1/4. If we add pi to it, what that ends up doing is it creates a negative of that y value. So by rotation, we have negative 1/4. Sine of theta plus 2 pi, this is a coterminal relationship, so we have the exact same ratio. Sine of negative theta, we can look at this as an odd function. Sine of negative theta will be the negative of sine of theta. Cosine, if we do the same, actually, I did cosine here, so let me keep this as cosine. Pardon the error on that one. So if I do this as cosine, cosine is the x value. If I add theta to that x value, or add pi to that x value, we add 180 degrees. So that gives us the negative of that x value, so by rotation. The cosine of theta plus 2 pi, once again, by adding 2 pi, that's a coterminal relationship, so we have the exact same y value, or x value. Cosine of negative theta, if we go below the x-axis, the x value is going to be the same, so we end up with 2/3. So we could treat this as an even function. Cosine is even, so cosine of negative theta is the same thing as cosine of theta. Secant, because secant is related to cosine, what I did was if the secant is 5/2, I know the cosine is its reciprocal, 2/5. So the x value is 2/5. By subtracting pi, that means by rotation, we are going to have the negative x value. By adding 10 pi, that's coterminal because we're adding 2 pi 5 separate times. So coterminal relationship means we have the same ratio, the same cosine ratio. And secant is an even function, so secant of negative theta is still going to be 5/2. Tangent, however, something slightly different that's going to occur with tangent. If we subtract pi, we end up with, if we use that periodic or that rotation, the slope of -7/5. So if I see the slope of -7/5, which say this looks like that. So let's see this in quadrant 2. So if my theta gives me a slope of -7/5, by subtracting pi, that takes me down here, meaning I have the exact same slope. By adding pi over 2, what that does, and this is very, very specific to tangent that I like to point out, by adding pi over 2 to that angle, which would actually be over here, we are adding a 90-degree angle. So what that does is it creates a perpendicular slope. Perpendicular to -7/5 is 5/7. And then we get a series of properties. Why are all these values what they are? The sine of 2 pi over 3 plus the sine of 4 pi over 3. What we could do with this problem is we could do this numerically because we do know the sine of 2 pi over 3, which is square root of 3 over 2. Sine of 4 pi over 3 is negative square root of 3 over 2. So these will end up equaling 0. But what happens if it's an unknown angle? If it's an unknown angle, I have the sine of pi over 5 plus the sine of 9 pi over 5. what I'm doing here is, if I look at this, I'm saying, okay, I know that the sine of pi over 5 has a certain y value. What's the relationship between pi over 5 and 9 pi over 5? Together they add up to 2 pi. So what that means is, if we look at this as 2 pi minus pi over 5, we get the 9 pi over 5, which gives me the negative of the y value. One of the big cautions is you are not allowed to add those two angles together and say this is the sine of 2 pi. I don't care that we have the same answer. If you add those two angles together, you're doing something incredibly wrong. And that'll actually show up in part C. So if you tried to add pi over 7 to 6 pi over 7, you get the cosine of pi, which is -1. That's not the answer to this problem. The way that we do this problem is we look at what's the relationship of the angles. Remember, I told you right at the beginning, we're going to be looking at the relationship of all these angles and using the geometry of the circle to help us understand these values. The pi over 7 and 6 pi over 7, they are related as pi, but that's because they are both pi over 7 off the x-axis, which means that pi over 7 has a positive x value, 6 pi over 7 has a negative x value, which they're the same x values and they add up to 0. For D, pi over 8, 9 pi over 8, they are off by pi as well. And because they're off by pi, that's a rotation. So you end up with the same slope subtracting to get 0. For E, we could do this one numerically, or we could do this geometrically. So numerically, the secant of pi over 4, secant is the reciprocal of cosine, so that would have been the square root of 2. The secant of 5 pi over 4, we are now in quadrant 3, so that's the negative square root of 2. That does add up to 0. So we could do that numerically, which is this approach, or we could do it more of like algebraic and geometry together, that secant is the reciprocal of the x value. So if you look at the secant as a reciprocal of the x value, then if you look at the geometry by adding a pi rotation, they're going to be opposite values, which ends up being 0. Same thing for cotangent. Hey, we don't know these actual angles, so that tells me it's going to be a geometrical relationship. Because those angles are off by pi, we take the reciprocal of the slope and subtract itself, because if you remember, tangent is going to be the same value if you add a pi rotation. For G, the same sort of scenario. You have -4 pi over 7 and you have +4 pi over 7. We don't know that angles, which tells us it's the geometric relationship. So we have that negative y value and we have that positive y value, reciprocate them and add them together to get 0. You could also look at this as an odd function. So if you look as an odd function, this is the negative cosecant of 4 pi over 7 plus the cosecant of 4 pi over 7. So that shows that we really don't care what those values are because they're going to be opposites and they add up to be 0. For H, you can use odd relationships as well. You can say this is minus the tangent of 2 pi over 5, since tangent is odd, and those subtract out to be 0. If you look at them as geometrically, slope in quadrant 1, and then this slope in quadrant 4, there are opposite slopes, which add up to be 0. So now looking at that geometrical relationship, we are going to build in a little bit more geometry, but we are going to go a little bit more algebraic. And to start off with, what I've done is I've done a quick review. If you remember what we did last time, sine of theta is y over r, cosine of theta is x over r, tangent of theta is y over x. And then we have our reciprocal relationships. Now, what that allows us to look at is all the trig ratios are positive in quadrant 1. In quadrant 2, however, only the sine and the cosecant are positive because both of these are associated with the y values. Both of these are associated with the x values, so they're negative. And both of these are associated with slopes, so they're negative. In quadrant 3, our slopes are now positive, but both the x value and the y value are negative, which is why those trig ratios are negative. In quadrant 4, that's quadrant 3, in quadrant 4, the x values are positive, but the y values are negative and the slopes are negative. So if you look at these as x, y, and r, you can determine whether these have positive and negative slopes. So the first problem we're going to do, we're going to look at and say, okay, where's secant and secant positive but tangent negative? What we're asking is where are both of these occurring simultaneously? We know that secant revolves around the x and is positive in quadrants 1 and 4. Tangent revolves around the slope, so it's negative in quadrants 2 and 4. Where do both of those occur at the same time? In quadrant 4. Where is sine negative and cotangent positive? So this is a slight different representation, but same kind of idea. Sine is negative because of y. It's negative in quadrants 3 and 4. Cotangent is positive where the slopes are positive, which is 1 and 3. So where both occurring at the same time, that would be quadrant 3. And the reason why we want to do that is because then we will say, okay, so given our cosine and our sine, so cosine is positive and sine is negative, what quadrant do those occur at? That would be quadrant 4. So then, because I have both ratios, I can actually write these ratios, and I tend to draw this out. You could do this as, okay, cosine is x over r, sine is y over r, and you can identify your x is square root of 5, your y is your negative 2, and then your radius is 3. So you're welcome to do that, and then you can write out those trig ratios. I like to see the geometric approach, so I tend to always draw out my triangle, because specifically it helps if my sine ratio is negative, it's the y value that's negative and not the radius that's negative. So it helps identify what is positive and what is negative. And it really just reinforces the fact that we're in quadrant 4. So the sine is our y over r, and then reciprocate it for cosecant. Cosine is x over r, and reciprocate it. Don't forget to rationalize. Tangent is y over x, and reciprocate it and rationalize. For problem number 7, this time I'm only giving one of the ratios. I'm giving one of the ratios, but I'm also saying secant is negative. So first thing again, what quadrant do both of those occur at? Tangent is negative in 2 and 4, and secant is negative in 2 and 3. So together they're both negative in quadrant 2. So this tangent ratio, tangent is y over x. Because we're in quadrant 2, as you see in the green highlight, it's the x value that's negative, not the y value. So it's the x value that's negative, the y value is positive. What we don't have is the radius. So if you remember last time, we found the radius by saying x squared plus y squared. I did that, and I got my radius as the square root of 34. And now I have my x, y, and r that I could use to find all 6 of my trig ratios. There are some nasty radicals and fractions here, but it's the exact same ratios that we had before. Sine is y over r, cosine is x over r, tangent is y over x. Cosecant, secant, and cotangent are all the reciprocals of those. Same thing for problem number 8. Secant is positive, which would be quadrants 1 and 2 because it's the x. Sine is positive in quadrants 1 and 2. Sorry, secant is positive in 1 and 4. Sine is positive in 1 and 2. So together they're both positive in 1. Secant is r over x. So that means the radius is 4 and the x value is 1. What we're left to find is the y. And we can do that by x squared plus y squared equals r squared. Now y should be the positive square root because we're in quadrant 1. And once I know that, sine is y over r, cosine is x over r, tangent is y over x, etc. Problem number 9, cotangent's negative and cosine's negative. That should be quadrant 2 because cotangent is a negative slope and cosine is a negative x value. So with that in mind, if cotangent's negative, keep in mind that x over y, since we're in quadrant 2, the x value is the one that's negative and the y value is the one that's positive. If cosine was positive, we would have been in quadrant 4. So if that was positive, we would have been in quadrant 4. Then it would have been the y value negative and the x value positive. But anyway, we are in quadrant 2. Our radius is always a positive value. So x squared plus y squared equals r squared again. And we have the same thing occurring. X over, or y over r, sine is y over r, cosine is x over r, tangent is y over x, and reciprocate each of those. Which leads to some of our identities. When it comes to our identities, what we're looking at is, I've been using pretty extensively our trig identities that are reciprocals of each other, so our reciprocal identities. Sine is 1 over cosecant, cosine is 1 over secant, and tangent is 1 over cotangent. We have our quotients, and these ones we haven't talked about, but tangent is y over x, and the reason why it's y over x is because it is sine over cosine. Cotangent is x over y, which gives us cosine over sine. Hopefully that makes sense. We're going to be using that a lot more extensively. Then we have our Pythagorean identities. With our Pythagorean identities, those stem from, and the most important one that we have is sine squared plus cosine squared equals Sine squared plus cosine squared equals 1. The reason why sine squared plus cosine squared equals 1 has to do with the fact that we have a triangle on the unit circle. So the x value is the cosine, the y value is the sine, which forces cosine squared plus sine squared to actually equal 1 by Pythagorean theorem. That's why they're called the Pythagorean identities. Now, to get the second Pythagorean identity, tangent squared plus 1 equals secant squared, we will take the sine squared plus cosine squared equals 1 and divide everything by cosine squared. So sine squared over cosine squared is tangent. Cosine squared over cosine squared is 1. 1 over cosine squared is secant squared. So we have tangent squared plus 1 equals secant squared. Now we can have all the different relationships where if you want to say what is secant squared minus 1, that's tangent squared. If you subtract both secant squared and 1, you get tangent squared minus secant squared is negative 1. So you have those Pythagorean relationships as well. I tend to stick with sine squared plus cosine squared equals 1 and develop the tangent squared plus 1, and then develop the 1 plus cotangent squared. And the way that I do that is by taking sine squared plus cosine squared equals 1, dividing it all by sine squared, and we get 1 cotangent squared cosecant squared. So the problems that we get from those, if we have sine squared of any angle plus cosine squared of any angle, that should equal 1. For part B, if we have 1 over cotangent squared, 1 over cotangent squared we can write as tangent squared, and now tangent squared minus secant squared, that's where I went back up to my manipulation of that second Pythagorean identity, and I get negative 1. Cosine squared of 24 plus sine squared of 384. First thing I have to do is recognize, hey, these angles aren't the same, but they're off by 360. So if I use the coterminal relationship that sine or 384 and 24 have the same sine ratio, then I have cosine squared plus sine squared, which then I know as well. Last but not least, we could look at these as functional relationships. So this is going to be the stepping stone that we're going to use to actually graph sine, cosine, and tangent as functions. So if we have f of theta is going to be the sine of theta, and I'm told that theta is 2 pi over 3. So what this means is, what is f of 2 pi over 3? Meaning, what's the sine of 2 pi over 3? And we should know that value really well. That'd be the y value at 2 pi over 3, which is square root of 3 over 2. We could also say, hey, let's do some manipulation of that angle. So what's half of that 2 pi over 3? That would be 1 pi over 3. And the cosine of pi over 3, that would be the x value of 1/2 because we're in quadrant 1. We could also double it. So tangent of 4 pi over 3, tangent of 4 pi over 3, we are now in quadrant 3. That would be the square root of 3. I'm looking down here and the slope here is the square root of 3. For part D, pi minus theta, we could start using some of our rotational aspects here if we really wanted to and say, I know the cosine is negative 1/2 at 2 pi over 3. So we could use that rotation of pi and its reflection too. But if we use that, we can get the positive value 1/2, or we could do it numerically. Pi minus 2 pi over 3 is pi over 3, and the cosine there is 1/2. F of 3 pi minus g of 3 pi. So 3 times 2 pi over 3 is 2 pi. Sine of 2 pi is 0. Cosine of 2 pi is 1. So 0 minus 1 is negative 1. For f, g, and h, what we could do is we can use either the fact that sine is an odd function, and f is the sine function again. So f is the sine function. Since sine is odd, f of negative theta plus f of theta plus f of negative theta should equal 0. We still can do this one numerically though, if we really wanted to. Cosine is even. So one of the things that we could do with cosine if we really wanted to, we could say, okay, g of negative theta is the same thing as g of theta. So I could double g of theta. So 2 times the cosine of 2 pi over 3 is 2 times negative 1/2, which is negative 1. Or you could do them individually. Now, which one's faster? This is where I think the geometry tends to be a little bit faster, but we still need to know all of our unit circle angles. For h, tangent is an odd function, so this should end up equaling 0. That's where it's very faster to do it geometrically. So that should equal 0. But we could also do it numerically. Tangent of 2 pi over 3, tangent of negative 2 pi over 3, which does equal 0. As we come to the end, Same kind of thing. We could either do it numerically, or we could do a rotation, which shows it's going to be the negative sine value. For g, cosine, we could do it numerically, or we could do a rotation, which makes it the negative x value. Tangent, we could do it numerically, or by doing the rotation, you end up with the exact same value. For h is tangent by adding pi over 2. This is one that we can do numerically, or if you remember, the opposite reciprocal, because this is a 90-degree rotation. So whatever that angle is, it ends up being a 90-degree rotation off of it. And then, oops, that should not be number, or that one should be 12, but this one should be 13. For 12, if we show that functional relationship, we could say, okay, I don't really care what the angle is, but I know that the sine ratio is 1/5. By saying f of negative a, that tells me because it's not a function, I should have the negative of that 1/5. By adding pi, it's that pi rotation, which is where we get negative 1/5 as well. So that's the negative of the y value. And then on this example 13, tangent one more time, we are given the tangent ratio of 7/4. F of negative a, because tangent is odd, it's going to be the negative of that ratio that we found. By adding 3 pi, that means we are going to be adding 1.5 rotations. So we have the same slope, which is 7/5 or 4. And one more time, by adding pi over 2, that would be a 90-degree rotation off that slope, which is the opposite reciprocal. So hopefully you enjoyed today's notes, and we'll see you next time.